So to this point, we've dealt with sum and difference formulas. We've dealt with double angle formulas today. It's a half angle formula. And we use these to find exact values of non-unit circle values that can be expressed as half of a known unit circle value. For instance, the cosine of 22.5 is half of 45. Likewise, if I have the cosine of pi over 12, that's just the cosine of half of pi over 6. Now, it's not just as simple as multiplying a half to the cosine value of pi over 6. There's an identity that goes along with it, and let's give you those identities. I'll show you where they come from because they can be obtained pretty easily through a verification process. We start all of these with the cosine of 2x and some form of its identity. So let's use the cosine of 2x is equal to 2 cosine squared minus 1. I can take and add 1 to both sides of the equation. Did that in this line. Then divide both sides by 2. That's done here. Square root both sides, take the plus and minus. And here's where the small trick comes in. We're going to let 2x equal this delta, right? Therefore, I can say that x is equal to delta over 2. And that's just by a division. So, therefore, if I say delta is equal to 2x, then I can say that this x is equal to delta over 2. So what we have is we have our half angle identity here. The cosine of something over 2 is equal to plus or minus the square root, and that's going to be dependent upon which quadrant you're in. The cosine of whatever that angle is plus 1 over 2. So that's the cosine of a half angle identity. The sine identity, again, we start out with the cosine of 2x equaling 1 minus 2 sine squared of x, but we're going to use sine this time instead of cosine because that's what we're looking to end up with is a sine identity. We add or subtract 1 to both sides. In the first step, divide by negative 2. Notice, since we're dividing by a negative, the signs switch. Square root both sides as we did in the other problem. Make the substitution of 2x is equal to delta. Therefore, x is equal to delta over 2. Make those substitutions into the problem. So instead of 2x, we now have delta. And instead of x, we now have delta over 2. And there's my half angle identity for sine. The sine of half of an angle is equal to 1 minus the cosine of that angle over 2. Moving through, we now take a look at the tangent of this. And tangent is equal to the sine over the cosine. So all I really did was put the known sine value, which is 1 minus cosine of x over 2, over square root of 1 plus cosine of x over 2, which is equal to 1 minus cosine over 1 plus cosine, all square rooted. And that's my tangent identity. Those is probably easier to know rather than to prove, so you might as well get those to memorization. So let's take and find the cosine of pi over 8, which we know is equivalent to half of pi over 4. And the cosine identity states, find out the quadrant it's in, that will determine positive or negative. And that happens to be in the first quadrant, so it's positive. Then I have 1 plus the cosine of the angle, and my angle is pi over 4, over 2. And this is equivalent to 1 plus root 2 over 2 over 2. I'll multiply by the reciprocal here, so I'm going to multiply by a half. And I get 1 over 2 plus root 2 over 4. That's all rooted. And that's equivalent to 2 plus root 2 over 4, which is all rooted. The square root of 4 is 2. So this is equivalent to the root of 2 plus root 2 all over 2. Next example's somewhat similar. We have a sine identity this time, and this is the same as the sine of half of 30 degrees. So again, we find out the quadrant that's in, and 15 degrees would be in the first quadrant, so this is a positive. And 1 minus the cosine of the angle, which is 30 degrees, all over 2, which is equivalent to 1 minus root 3 over 2, all in a radical. Multiply by the reciprocal, and I get a half minus root 3 over 4, all in a radical, which is 2 minus root 3 over 4, all within a radical. Square root of 4 is equal to 2, so that's the root of 2 minus root 3 all over 2. In our next example, looks like we're dealing with a triangle problem, and we're talking about an angle in the fourth quadrant, so let's just draw an angle in the fourth quadrant, A, that has a cosine value of a fifth. And if I want to find my y value, which I'm probably going to need to do, I'm not sure, but well, actually I don't need anything in this, because I'm looking to find my sine of a over 2 value, and sine of a over 2 is just equal to the root of 1 minus cosine of a over 2. Since I'm already given the cosine of a, I can just go in and plug this in right now. That's 1 minus cosine of a is 1/5 over 2. Once again, I'll multiply by my reciprocal, which is a half, and get a half minus 1/10. It's all rooted. This is 5 over 10 minus 1 over 10 rooted, which is the same as 4/10 rooted, or 2/5 rooted, which equals root 10 over 5 after I'm done rationalizing, and then I'm done. If this wasn't straight cosine value, I'd probably have to go find the missing pieces in this triangle to get the problem done. So now let's do a verification. In this problem, I'm looking for the tangent of theta over 2, which I know to be 1 minus cosine over 1 plus cosine. I'm keeping that in mind, all rooted. And I'm going to try to get that from this, which seems a little tough. So maybe I'll work with this identity and try to make it into this. So I'll go ahead and do that. I know that the tangent of theta over 2, or x over 2, is equal to 1 minus cosine over 1 plus cosine. Anytime I see binomials, I look to do conjugates. So if I multiply by root 1 minus cosine over root 1 minus cosine, notice what I have. I have 1 minus cosine squared, square rooted, all over the square root of 1 minus cosine squared, because that's FOILing to get a difference of two squares. The square root of a squared term is always going to be that term, so that's 1 minus cosine of x, which is exactly what I want. And the square root of 1 minus cosine squared, well, 1 minus cosine squared is equal to sine squared. And if I square root a squared term, it's just that term. So this is 1 minus cosine over sine, which is what I wanted.